All right, let's get started. So, welcome to the second lecture of CS294. A few logistical notes. So first, if you're enrolled in the class, again, just make absolutely sure you're signed up for Piazza. We try to automatically sign up everybody who's enrolled, but if you use kind of a different email address for Cal Central or something like that, maybe those emails aren't going to. Do make sure you're signed up for Piazza because we're using that to distribute all the homework assignments, course announcements, and so on. So if you're enrolled in the class, really please make sure of that. Homework 1 is now out. And actually, all of the material that you need in order to do homework 1 will be presented in today's lecture, unless I run out of time. But most likely, I'll get through everything in today's lecture. So you can, at that point, you can start on homework 1. And good idea to start on that early, especially if you're not completely sure about whether you have kind of the right background for the class. Give that a shot, see how it goes. Maybe come into office hours if you're stuck a little bit. But do make sure you start on that. And also, if you start on homework 1 and you decide that you maybe need a little bit more help with TensorFlow things, Greg Kahn is going to be teaching a lecture on TensorFlow and other kind of neural network training tips and tricks on Wednesday next week. So the regular lecture time on Wednesday next week will actually be a lecture on TensorFlow usage. So get started on homework 1 before that. And if you have questions, if you have concerns about things, bring those to lecture and ask Greg about that. And a good idea to start thinking about your final project groups early. So we're going to release the assignment for the final project soon, but it's going to be you can work in groups of 2 to 3 students. You can have larger groups if you want, but if it's more than 3, you should ask us first. You can also work by yourself, but if you want to form a project group, which is generally a good idea, you can start on that right away. The sooner you start, the sooner you get your group together, the sooner you can start thinking about ideas for your final project. Okay, today's lecture. Today, we're going to talk about imitation learning. So we're going to start off with a definition of sequential decision-making problems. We're actually going to work our way from regular supervised learning to sequential decision-making. We're going to talk about how we can set up an imitation learning problem, which is basically supervised learning for decision-making. We're going to talk about whether direct imitation works or not, and when it works and when it doesn't work, how can we make it work more often, and so on. And then we'll conclude with some case studies of recent work in kind of deep imitation learning, using imitation learning to learn skills from images. And if we have time, we'll also do a little bit of theory towards the end to try to analyze some imitation learning methods. And then we'll talk about what's missing from imitation learning and really motivate why we should also be looking at autonomous decision-making with reward functions in RL, which we'll begin covering next week. So the goals for today's lecture will be to understand definitions and notations, understand basic imitation learning algorithms, including behavior cloning and Dagger, which you'll need for homework 1, and understand their strengths and weaknesses, so where one method might be appropriate versus another one, and what kind of failure modes you might expect when you try to use these things in practice. Okay, let's start with some terminology and notation. So what I have here on this slide is actually kind of the rough anatomy of a supervised learning problem, but using some of the notation that we'll see in reinforcement learning. So in a supervised learning problem, let's say it's image recognition, you have some kind of input that goes in, you have some kind of output that you care about. So in this case, the input consists of pixels in an image, so this is a picture. And the output is a categorical random variable, in this case, the label of the object in that picture. So you get some pixels, you don't really know what those pixels are, it's just a huge array of numbers, and then your job is to figure out, well, is this a picture of a tiger cat, a jaguar, a lynx, or whatever other category you might have in there. And the thing in the middle, the thing that goes from one to the other, is the model that you want to learn. So a model, in this case, is basically some way to parameterize a probability distribution. And it's a conditional probability distribution, so it's conditioned on the input, which is the image, and it's a distribution over the output, which in this case is this categorical random variable. So we're going to attach some symbols to these things. We're going to say our input we're going to call it O for observation. That's the thing that you actually observe. Your output, we're going to call it A for action, which in this case is a categorical random variable that can take on one of n values, where n is the number of possible image labels. And this distribution that we're learning, we're going to call it pi, and it's a distribution over A conditional on O. And this distribution has some parameters, which we're going to denote theta. So in the remainder of this course, when you see theta, that refers to parameters of some parameterized distribution. And we can choose many different ways to parameterize this distribution. So we could, for example, make it linear in the observation. That would not be a very good idea for images, but you could do it. You could basically attach a weight to every pixel and say, okay, this is like, if this pixel is on, it's probably a tiger. If this pixel is on, it's probably a cat. But that's not a very good way to build a robust classifier. So if we want to do kind of good modern computer vision, we would probably use some very powerful function approximator to represent this distribution, such as a deep neural network. So in that case, theta refers to the weights in the neural network, literally the weight matrices at every single layer. But it's important to remember that what that neural network is really doing is it's parameterizing a probability distribution. And there are other ways to parameterize probability distributions also. Okay, so now if we want to go from this supervised learning problem formulation to a sequential decision-making problem, then we need to add something sequential and something that involves decisions. So first, let's deal with the sequential part. Let's put a subscript t on everything. That denotes that all these things are part of a temporal process. So you observe the observation O at time step little t, and you output your action A at time step little t. And this is part of a process, so the action that you output will potentially affect the next observation you will see. So if you fail to recognize the tiger, then maybe you'll see an angrier, bigger tiger next time as it gets closer to you, but if you succeed at recognizing, maybe you'll see something a little more desirable. And then you can change these, this output. Instead of maybe recognizing the tiger, you want to output also a categorical random variable that denotes actually the action that you're going to take. There's a bunch of things you can do when you see the scene. It's important to pick the right one, but we haven't really changed anything about the learning problem. We've just changed the meaning of these things. So if you have actions and those actions are discrete, exactly the same setup as the classification. It's just a categorical random variable, and you're outputting a distribution over that variable given your observation. So everything is straightforward. But remember that this thing is this network is parameterizing a distribution, so you can use other classes of distributions too. If you, for example, have a continuous action, maybe instead of choosing from among a menu of choices, you're actually choosing which way you're going to run to try to get away from the tiger. Maybe you output, let's say, a real valued number to determine which way to run. Now you just need to choose a representation for pi that can parameterize continuous random variables. And there's many choices for this too. For example, you can have pi output the parameters of a Gaussian, the mean and the variance. And that's a perfectly legitimate way to output a distribution over continuous actions. So we could do that also. Okay, so what are the concrete things that we're getting out of this as far as our notation? We have O subscript t, which is our observation at time step t. That's what your policy actually gets to see. That's what forms the basis for its decision. We have the action at, that's what you're going to choose at time step t. We have our policy, pi subscript theta at given ot. So the policy is a conditional distribution over a given o, and it has parameters theta. There's another thing that we haven't actually talked about yet, but that's actually very important to understanding sequential decision-making problems, which is the state. So your policy, in the most general sequential decision-making setting, observes an observation. But underlying these observations, there's something called states, which we'll typically denote with S. And states also, of course, have a time step. You don't always observe states, although sometimes we will simplify our problem setting and say that, well, O is equal to T, so you actually have a policy that depends on S, and sometimes we'll refer to this as fully observed. So oftentimes in this course, you'll see me write A given S. Keep in mind that in many of those cases, that can also be A given O if you have a partially observed setting. But in general, there is a very important distinction between S and O. O is what you actually get to observe. S is the underlying state of the world. So what is the underlying state of the world? Well, let's look at this picture for a second. This is, in this picture you can see a cheetah. It's chasing a gazelle. When a computer looks at this, the computer doesn't see a cheetah and a gazelle. It sees a big 2D array of numbers, right? It sees the pixels in the image. Now you know when you look at this picture that somewhere in there there's a cheetah and somewhere in there is a gazelle, and your understanding of the physical world suggests that these things have positions, they have momentum, they have all these physical properties, but those are actually hidden inside the image. You need to actually process the image to get those out, and your brain happens to be very good at that. The computer needs to learn how to do that. So the observation here is not positions and momenta of cheetahs and gazelles. The observation is the image pixels. So that's the observation. But underlying that observation, there is some state. There's some kind of concise summary of the physical phenomena going on in the world. And what makes the state a state is that the pixels in the image, the observation, is a consequence of the state. So the reason that you see the cheetah-shaped pixels over here is because the cheetah is located over here, not the other way around. Okay, we can make this a little bit more formal. So formally, the distinction between state and observation is that the state is basically the, well, you'll see the graphical model on the next slide. The state is actually the sufficient kind of summary of what's going on in the world that you can use to predict the future. The observation is a consequence of that, but it might be a lossy consequence. So let me just explain the lossiness and partial observability really quickly. If a car drives in front of this cheetah like this and hides the cheetah pixels, you might not be able to tell from looking at the picture where the cheetah is, but the state of the cheetah hasn't actually changed. So the state remains the same, even when you can't deduce that state from looking at the observation. And that's a very important distinction. So here's the more formal description of what's going on here. We can draw a graphical model to relate these variables to each other, to relate the state, the action, and the observation. And it's the graphical model is a dynamic Bayesian network, so it goes forward through time. And at each time slice, you have an O, an S, and an A. The mapping from O to A, the distribution over A given O, that's described by the policy. So the policy is basically a conditional probability distribution in this graphical model. The edge that goes from S and A to the next S, that's sometimes referred to as the transition function, the transition dynamics, or the dynamics function. That basically tells you how does your current state and your current action influence the next state. And the observation is produced from the state. So something about the state gives rise to the action, potentially through a random and lossy mapping. So it's basically a distribution O given S. Now, those of you that remember how independence in graphical models works, from looking at this picture, you might already start to suspect that there's some interesting independence relationships that happen with states and with observations. So one of the most important independence relationships in these sequential decision-making problems is that if you observe ST, let's say you observe S2, for example, you observe this node, someone tells you this is the state, this is the precise position, momentum, and so on of the cheetah and the gazelle. Then S3 becomes conditionally independent of S1. And in particular, what that means is that if you know the present, no additional information about the past will tell you anything about the future. If you perfectly know S2, then knowing S1 doesn't help you predict S3. And this is very important in sequential decision making because what that implies is that if you're trying to make a decision, if you're trying to choose A2, and you already know S2, then nothing about S1 or any preceding state will help you make a better decision. Because knowledge of S2 is all you need to predict everything about the future because of that conditional independence. Question?
The first one, given OT in the policy, OT is given to you, but ST, how do you compute it somehow?
Yes. So in general, in the most general sequential decision-making setting, you never actually observe the state. We will sometimes have algorithms that we'll discuss in this class that operate in a fully observed setting. So if you see something like this, that just means, okay, I'm talking about the fully observed setting. But in general, the most general case is the partially observed setting. And in fact, people will often use algorithms that are designed for fully observed problems like this, but still use them for partially observed problems, which technically is incorrect and can cause you some trouble. But depending on how partially or fully observed it is, that might be sufficient. So if you have that setting with the cheetah and the gazelle, and you never have the problem of the car driving in front of the cheetah, and you can always tell where it is, maybe that's okay. But important to remember that if you want things to be technically correct, to recognize whether you're in this setting or this setting, and which of these settings can your algorithm really accommodate. So the imitation learning algorithms we'll talk about today, they really work with the partially observed setting. Later on, we'll talk about things like Q-learning, which require a fully observed setting. All right. So next state is conditionally independent of the previous state, given the current state. The same is not true for observations. So if you observe O2, and you do not know what S2 is exactly, so you only observe O2, then knowledge about previous observations might actually give you helpful information. So it might be that if you observed O2 and O1, you can be smarter about choosing A2 than if you had only observed O2. And this makes perfect sense. If you're in that situation with the car driving in front of the cheetah, if the car is currently in front of the cheetah, that's O2, you don't know where the cheetah is, maybe you can't make a good decision, but if you also looked at the previous frame where the car was not yet in front of the cheetah, you can get some additional information from that. So if you're observing states directly, knowing the current state is sufficient and there's no benefit to be gained from getting previous states, but if you're observing observations, then previous observations might in fact give you additional information. So this independence property, the fact that S3 is conditionally independent of S1 given S2, is referred to as the Markov property. And we'll talk about definitions of Markov chains and so on next week. A little aside, so some of you who have more of maybe a control theory or robotics background might have seen notation that is instead of SA that uses X to denote state and U to denote action. So this notation of using S and A was popularized in the world of Markov decision processes by Richard Bellman, and makes sense why we use S and A. S is the first letter of the word state, A is the first letter of the word action. In control theory, sometimes it's a little more common to use X and U, X to denote state because it's a symbol often used for unknown variables, and U for action because it's actually the first word for control in Russian, uправление. So this kind of notation was popularized by control theory folks, people like Lev Panterягin. But don't be confused by this. It means exactly the same thing. So if you read some paper and you see U and X, it's just the same as A and S. There's no difference. And we'll use this notation in this class. But if I occasionally slip up and have this in a slide, just don't worry about it. Okay, so now let's talk about imitation learning. So we described our notation. We talked about how we have observations and actions. We'll transform this problem a little bit into something that's maybe of a little bit more practical value. So instead of talking about tigers and running away from them, let's work with a kind of a simple driving example. Let's say that your observations are images from a dashboard camera in your car, and your actions are the steering commands. So you can turn the steering wheel left or right. So one of the ways that we can go about actually training Pi here is we can do exactly the same thing that we do in supervised learning. Don't worry about the fact that it's sequential and so on. Just collect data and do supervised training. So in particular, you can get a human driver, get them to drive this car, record images from their dashboard camera, put an encoder in the steering wheel and record the turning of the steering wheel, and you get a data set. And in that data set, at every point in time, you record the observation O and you record the action A. So you store that training data on your hard drive, and then you use it with your favorite supervised learning algorithm. So take a big ConvNet and do stochastic gradient descent with something like momentum, and out comes your policy pi theta A given O. This is very straightforward, and this kind of algorithm is sometimes referred to as behavior cloning because you're essentially trying to clone the behavior of the human demonstrator. But algorithmically, implementation-wise, it's basically exactly the same as regular supervised learning. And this is a very valid way to train policies. It's one of the simplest things we can think of if we're starting off from supervised learning. So then we can ask this question: does it work? In general, if you do exactly what I describe on this slide, in general it does not work. Does anybody have any ideas why this might not work? What might go wrong? Yeah?
Something new that wasn't in the data.
Okay, so one answer is you might see something new that was not in the training data. So maybe you never saw big white trucks, and now suddenly you see a big white truck, and the policy doesn't know how to respond. Any ideas about what else might go wrong? Yeah?
People make mistakes.
People make mistakes, yeah. So these actions that you see in your training data, they might actually be bad actions. There might be some really bad actions in there, and then your policy will basically copy those bad actions. Any other ideas? Yeah?
There's
there's no temporality. So for the same images, you could have two actions, but it depends on the previous action.
Okay, this is a good one. I'll actually talk about this later in the lecture. So the answer for those of you that didn't hear it is, you might, in the data, you might have two different actions for two very similar images, because for a person, they might be making that decision based on something they saw in the past, but your policy is only looking at the present. And we'll talk about this and we'll discuss some solutions. Any other ideas? Yeah.
It might be hard to use gradient descent to find the solution.
Mm-hmm. Why might it be hard to use gradient descent?
Because the optimization problem isn't very convex-ish.
Right. So with this kind of setting, okay, you're contending, in addition to all the unique problems of learning policies, you're also contending with all the usual problems of doing supervised learning. So if you're using some huge overparameterized function approximator like a big neural net, and you have things, non-convexity, saddle points, etc., you have to address them in your supervised learning algorithm just the same way as you would in any other supervised learning problem. And that's not always very straightforward, especially if you have really complex models like recurrent neural nets. So that can happen too. Okay, there is actually a more basic problem that tends to happen that is unique to the sequential decision-making setting. And then let me try to explain this problem with a little illustration. Then towards the end of the lecture, if I have a bit of time, I'll actually work out a more formal derivation for this. But I'll start with just the intuitive one. Let's say that you have a very simple setting. You have a one-dimensional state, just so I can draw it on a picture. And this axis represents state, this axis represents time. So this black curve, this is a trajectory. Imagine somebody controlling a little agent on a 1D number line, and they're just moving left and right, and they generated this trajectory. Those of you that are familiar with physics, this is kind of like how you would draw a world line, basically. So this is a trajectory, right? Now, let's say that you use this trajectory as training data to train your policy. So at every point in this trajectory, it's a very small amount of training data, but let's say you use a small policy, so you're not going to overfit too much, but at every time step, you'll basically learn to copy the action this guy took. Now, no training algorithm is perfect, even on the training data, so you will incur a little bit of error. And it'll be a small amount of error. Let's say that you did a good job of learning, so the error is small, it's some small amount epsilon. And now what we're going to do is we're going to play back our policy. We're going to take our learned policy and we're going to run it forward. And it makes a tiny mistake. So this little red line, this is the first bit of the policy. For the first 20 time steps, it deviated just a tiny bit from that black line. Not very much, but it did deviate a little bit because it makes mistakes, small mistakes at first. But now look at what happens. When it deviates a little bit, it finds itself in states that are different from the states that were seen on a training trajectory. Initially, they're only a little bit different. But if it was making small mistakes over here when it was close to the training data, now it's further from the training data, so the mistakes will get a little bit bigger. And when the mistakes get a little bit bigger, it'll be even further from the training data, and the mistakes will get bigger yet. So for a long enough sequence, eventually these mistakes put it into even more unexpected states, which results in bigger mistakes, in even more unexpected states, and so on, until after a long enough trajectory, this policy might actually diverge quite far from the behavior that was seen in the training data. So if you'd like a little bit of intuition for this in the car example, if you're driving the car, maybe when the car is in the middle of the lane, the policy moves a little to the left, just a little bit, but now it's seeing a picture that's different from anything seen during training. It's seeing the car kind of a little sideways with the lane not going parallel to the lane. So now it's going to make a bigger mistake. Maybe it'll drift a little more to the left. And now it's seeing something completely different. Now the car's 45 degrees to the lane, so it's going to do something even more unexpected and eventually go right off the road. Okay. We'll talk about a way to do a little bit of math with probability distributions at the end of the lecture to explain this more. But does it work in practice? The answer is that in practice it can actually work. This is a video from NVIDIA research showing, initially they have their car doing some somewhat undesirable things, trained with imitation learning, exactly that supervised method I described before. But then they say, well, then we waited until March 2016 and collected a lot more data and didn't worry too much about the problems associated with imitation learning. And the thing kind of did something reasonable. So collect enough data, and it seems to kind of follow cones and follow roads and so on, seemingly without regard for mathematics. and so much so that you can kind of work up the bravery to actually put it on a road with other cars and hope for the best. Okay, so what's going on here? Why is this whole drifting thing not an issue here? It turns out that there are a number of different ways to address this issue, some of which are guaranteed to fix it, some of which are not guaranteed, but in practice often do fix it. The particular technique used in this paper is not guaranteed to fix the problem, but in practice is actually a pretty neat idea. So if you actually go and read this paper, you will see that it's all very straightforward. There's a steering wheel, there's a convolutional neural network that looks at images from a camera, but then there's something kind of funny going on. There's this kind of left camera, right camera, center camera, and if you actually read carefully through what they did, they have a really neat trick to mitigate this kind of drifting problem. What they do is the following. They say, well, we'll have one camera in our car that's pointed forward, and for that camera, we're going to learn to map from the image to the actual steering command, just like I described. We'll have another camera that's pointed a little bit to the left. And what we're going to do is we're going to take all of the steering commands and we're going to actually bias them to the right a little bit, and we'll train the network with these images with the user steering command biased a little to the right. Which makes a lot of sense, because if your car is drifting a little to the left, you'll just compensate by going a little to the right. And the same thing for a rightward-facing camera. We'll take all the images from the rightward-facing camera, take all the steering commands, and bias them a little to the left. So this essentially stabilizes the policy. It says when you start seeing things that are a little to the left of what you saw, compensate by steering to the right. So there's a little bit of domain knowledge. You have to know that when you're seeing things that are kind of going left, you should steer right. But it provides that stability that keeps you from drifting off the road. Now this is a little bit specific to this particular domain. But in general, the theme here is that you're teaching the network how to correct its mistakes. And you can do a more general version of this. You could, for example, say, well, maybe I have some way to generate not just a demonstration that will cause me to drift like this, but perhaps I can somehow obtain a distribution over trajectories, a distribution where the user's behavior is perturbed by some kind of noise, forcing them to correct that noise. So if we introduce noise into this, force the expert to correct that noise, then they kind of describe this full distribution, and then when your policy drifts a little bit from the optimal behavior, there are going to be some samples in the data set that had kind of qualitatively similar mistakes that'll teach it how to correct itself. In general, building out a full distribution like this analytically, of course, is difficult with humans because humans can't write down their distribution over actions. They can just do the task. They can't give you distributions. But if you're imitating, let's say, a computational agent, a planning algorithm, for instance, you can actually artificially introduce noise, force it to correct that noise, and then use that as training data. So you could, for example, imitate an optimal controller trained with some other technique and get stability. So here is one way you can do it. So you can take a sequence of states and actions, which will for shorthand, we'll denote that as a trajectory tau. You can build a distribution over trajectories using some planning algorithm. We'll talk later on in the course about how to do this using linear quadratic regulators, which are stabilizing controllers. And then you can construct the resulting distribution, sample from that distribution, get these samples that make mistakes and correct them, and use that with imitation learning to train policies that are stable. So using this, you can actually control fairly complex dynamical systems. This is a simulated humanoid in a physics simulator that learned to run using imitation learning, but by imitating a distribution of trajectories generated by constructing stabilizing controllers in the neighborhood of motion capture data. So we'll talk about this kind of stuff later on in the course. Okay. But so far, these things are all kind of heuristic in nature. It's saying, well, if you show left and right pictures and show it how to correct itself, or you generate some distribution with a lot of noise, maybe somehow things will work out. But can we construct an algorithm for imitation learning that actually, in the limit, is guaranteed to solve this problem, at least under idealized conditions? Well, in order to do that, we need to get a little bit more of an understanding for why the problem happens in the first place. So when we run our policy pi theta, what we're really doing is we're sampling from A given O. And this policy pi theta, it was trained on a distribution of observations that we're going to call P data. So the human drove the car, and the distribution of observations in that data set is called P data. So when you sample images from your training set, you're really sampling from P data. And maybe you have a fixed size training set, but that training set came from P-data. So in general, if you have enough data, you basically get good coverage on P-data. So regular supervised learning kind of generalization bounds will tell us good things about anything coming from P-data. We can reasonably assume that our error on samples from P-data will be bounded. But when we run pi theta, we actually observe observations from a different distribution, right? Because this pi theta will make these mistakes, which will cause it to deviate more and more. So the distribution of observations seen by the policy is this p pi theta of O, which is not in general equal to p data. So the reason that this whole problem exists is that p data is not equal to p pi theta, and perhaps one of the ways we can fix it is by devising an algorithm that will actually cause p data to be equal to p pi theta. So how can we do this? Can we make p data equal to p pi theta? Well, one way to do this is, of course, to train the perfect policy. If you train a policy that never makes mistakes, then it will never drift like this, and this problem will not occur. So in that case, p data will be equal to p pi theta. But training policies that don't make mistakes is very hard. So maybe what we can do instead is, instead of changing p pi theta to be perfect, maybe we can actually change p data. Maybe we can actually change our data set so that this distributional mismatch, this distribution shift, goes away. So instead of being clever about our pi theta, what if we can be a little more clever about p data itself, about our data set? So this is the idea behind the data set aggregation algorithm, or DAGR. So this is actually an algorithm that you guys will be implementing in homework 1. And it's a very simple algorithm. And the nice thing about this algorithm is that if you run it long enough and a bunch of assumptions hold true, then it's actually guaranteed to work. Now, of course, in practice with deep neural networks and stochastic optimization algorithms, there are no promises in life, but under nice convex assumptions, this is guaranteed to work. So here's the algorithm. Step 1, just like in behavior cloning, collect, right, so the goal, first of all, what is the goal of the algorithm? The goal of the algorithm is to collect data from p pi theta instead of p data, right? So then they'll be equal. And how are we going to do that? We're going to do it by just running pi theta and asking for the samples that we observe from pi theta to be labeled by a human. So that's going to require us to get these labels, which requires a kind of an interactive data collection protocol. So we'll actually run the policy and ask people after each time we run the policy to go back in and label all the images that we observed, which is a little bit more onerous, but then we'll solve this distribution mismatch problem. So step 1, just like in behavior cloning, collect a bunch of human data initially to get started. Human data consists of this data set D, which is O1, A1, et cetera, until you get to ON, AN, and use that to train your initial pi theta A given O, right? That's exactly the same as behavior cloning, so this is behavior cloning. Now we're going to add some more stuff to it. Step 2, run pi theta to get a new data set, D pi. So this basically means let your computer drive the car and see what it does. And we're not going to care about which actions it took, we're just going to be recording the images. So that gives you a new data set, D pi. Now we're going to ask a person to watch this video of the policy controlling the vehicle and ask it to label every single one of these images with the action AT. And this can be a little weird. Like, people can be pretty good at driving a car. They might not be so good at retroactively watching a movie and saying what the car should have done. But let's just assume we can do this, and we get labels. So now we have this funny hybrid data set where the observations came from the policy, but the actions actually came from the human. So now we have a labeled D pi. And now we're going to aggregate, hence the name data set aggregation. So we're going to say that our D now is going to be our old D union with this new D pi. And then we repeat. So we're going to repeatedly add data from the policy, labeled with optimal actions by the human, combine it with our old data set, and then retrain our network on that. And we'll just keep doing this. Now, if we keep doing this long enough, eventually, the majority of our data set, in fact, almost all of our data set, if we run this long enough, will consist of samples from pi, because you're not adding any more observations from the human. You keep adding observations from pi, run this long enough, eventually almost all the data set will consist of observations from pi, which means that in the limit, the distributional mismatch will actually be eliminated if you run it long enough, asymptotically. Yes?
Why don't you have to, from the beginning, union D pi? Why can't you just start like after
sampling from the policy, why
Mhm.
did you just start with dpi and just...
You mean just skip this step and just replace it with dpi? You could do that. In practice, it tends to not work as well. And the benefit of having a slightly, a substantially larger data set outweighs the cost of having a slightly lopsided data set. The actual proof of convergence for this algorithm is based on methods in online learning, where you actually would just do this. You wouldn't like run the policy for a long time. You just every single sample you keep adding to D. In practice, at least from what I found, the aggregation approach almost always works better. In fact, I don't remember ever seeing the case where discarding D makes it work better. But the formal reasoning is based on online learning algorithms. So for that, I would refer you to the Ross paper, which I'll have a full citation for at the end of the lecture. Any other question? Yeah.
At the beginning, is the first stage important? Like, can you start from 2 only on the first stage? Like, you run it from the beginning?
Yeah, so what you could do is you could just run a completely random policy right from the beginning. Technically, the algorithm still converges. In practice, it's hard to imagine why you would want to do that, because that basically amounts to saying, well, let's just let the car do random stuff, which will almost certainly cause it to do bad things early on, but in some cases you might want to do that, yeah. And the algorithm still has convergence guarantees in that case, yeah.
So after you aggregate, do you again recollect data from just the human only?
No. So I guess I just cross out the word human here, yeah, yes.
So when you talk about convergence, you're talking about converging to an optimal solution or suboptimal?
Yeah, optimal with respect to what is what you're going to ask.
Okay.
Yeah, so I'll describe what the objective of this is optimizing is at the end of the lecture. It's a little subtle because it requires introducing reward functions and so on, which I'll do a little bit later. Any other questions? Okay. All right, so that's basically the practical description of the algorithm. It's very, very simple. Here's an example of an experiment that was actually done in the paper that introduced Dagger for flying a quadrotor. So what they're doing here is the action is just this one-dimensional steering command, and they collect the data in exactly the way that you expect. They had a human fly the drone. They used that to initialize the policy. Then they let the drone fly itself. And then they have a person in the lab watching these videos and relabeling them with the actions that the drone should have taken retroactively. And they get the drone to do some pretty nice stuff, flying through forests, avoiding trees, and so on, in a fairly reasonable way. Okay, so what might be some of the problems with this algorithm? Does anybody have any ideas about potential downsides of using Dagger? Yeah?
You need a lot of humans to label. You need a lot of humans to label the data.
Yeah, so you need a lot of humans to label this data, and potentially you might be producing a lot more data here than you might have if you just did step 1. So that takes a lot of effort. Any other thoughts? Yeah.
Human might not always give like the right action from the observation. Like sometimes they have to just be there in the moment.
Right, so the human might not give you the right action from the observation, because when they're actually like driving the car or flying the drone, they're not actually doing this like Markovian thing where they look at a snapshot of the world and take an action. They're, as you said, they're there in the moment, so their brain is also part of a temporal process, a dynamical system, and so on. So it might be a very unnatural modality for a person. And this is very task dependent. So if you're like playing chess, for example, maybe a good chess player can just look at a snapshot of the board in the middle of the game and say, oh, this is a good move. But for something very dynamic like driving a car, maybe that's a lot harder. So it depends on the task. So in general, most of the issues with this algorithm really have to do with this third step of asking the human for the additional labels. And sometimes it's natural, sometimes it's not natural. And in practice, that's one of the big things that sort of limits more widespread applicability of this algorithm. Can we make imitation learning work without having to add more data? Can we get these things to work without having to have a human sit down and relabel observations seen from the policy? So in order to think about this, let's go back to what is the problem that Dagger was trying to solve. So Dagger was trying to solve this problem of distributional drift, distributional shift, which is basically illustrated by this picture, that if you start making mistakes, you make bigger and bigger mistakes, so you drift to a new distribution over observations. So what if the model was so good that it doesn't drift? And I said before that, of course, if you have a perfect model that never, ever, ever makes mistakes, then this problem goes away. In reality, for practical dynamical systems that have some degree of smoothness, maybe it's enough to just make very, very few mistakes. Maybe you don't need it to be completely perfect. Now, this is, of course, a little heuristic and involves some assumptions about how your dynamical system works, but maybe you can actually just solve the problem by having a better model. And in practice, this can actually work decently well. So you can actually improve your model to the point where it makes so few mistakes that direct behavior cloning works in some situations. So you need to be able to mimic the expert behavior very accurately. And in order to do that, it often helps to understand what are some of the ways in which, what are some of the properties that might make human behavior difficult to mimic. And of course, you have to do all this without overfitting. So you can't simply say, well, let's just make my model 10 million times bigger, because you still need it to generalize, but you need to be very accurate. And the good news is that there are actually things we can do. There are design decisions we can make in designing our model that will make it better at imitating human behavior without necessarily making the model overfit catastrophically. And we'll talk about a few things, kind of a few practical tips that tend to work well. So why might we fail to fit the expert data? What is it that people might do that might be difficult for these models to replicate? So one of the things, which I think somebody actually mentioned earlier in the lecture, is non-Markovian behavior. So even if we have a situation where we know the image, the observation, contains all the information we need to make an optimal decision, a person might still choose to peek at the past in making their decision, because people operate a little differently than computers do. Maybe people have bounded rationality, computational constraints, or maybe they're just lazy. They don't want to think very hard. So if they're currently turning to the left, even if there's something in the observation that currently suggests they should instead turn to the right, they'll just keep doing it because they've already committed to that plan. So even in situations where a Markovian policy could be sufficient, people might still choose to act in a non-Markovian way, and in practice very often do. People might also exhibit multimodal behavior, which is actually distinct from number one. So they might, even if they're doing something that's almost Markovian, they might just choose to do different things in similar situations just because. Today they're happy, tomorrow they're sad. Today their left hand itches, so they're going to turn the steering wheel to the right. Tomorrow their right hand itches, so they're going to turn the steering wheel to the left. All sorts of random reasons that are not observed by the policy might cause people to behave in different ways in seemingly indistinguishable situations. So let's talk about the first one, the non-Markovian behavior, and then we'll talk about the multimodal behavior. So if you're worried that your human demonstrators might be behaving in a way that depends not just on the present but also on the past, you can try to address this by making your policy depend not just on the present but also on the past. So a standard kind of feed-forward neural network, the kind that we might use for image classification, depends only on the current observation. If people see the same thing twice, so if this policy sees the same thing twice, it'll do the same thing twice, regardless of what happened before. And if this is not what your human demonstrator is doing, you can train a network that depends on all previous observations. So we can do this using all sorts of different neural network architectures, but probably the simplest and most popular design is to use a recurrent neural network. So how can we use the whole history? Well, we could, we have access to the whole history of observations. We don't want to feed all of these into a standard feed-forward convolutional network because we have a huge number of channels here. So we might have first too many weights, and the number of previous frames might vary. So what we can do is we can try to design a recurrent architecture. And there are many different ways to design it, but this is kind of a cartoon illustration of the simplest class of designs, where you have a convolutional encoder for each frame. You share weights across all the convolutional encoders, and then at the top you have some kind of recurrent neural network that will take in the output from this convolutional tower and will propagate it forward in time. So you have shared weights for your encoders, and for the recurrent state, something like an LSTM cell generally tends to work decently well. So if you're interested in this, look up long short-term memory, LSTM, fairly easy to set up. Generally, optimizing these kinds of models is a little bit more onerous as far as the optimization challenges, so they tend to require a little bit more tweaking to get right, just because propagating gradients through long recurrent sequences is difficult. But in principle, this kind of thing can provide memory to your model and make it possible to handle non-Markovian demonstrations. And I'll show an example of a paper that does this later on in today's lecture. All right, let's talk about the second one, the multimodal behavior. This one is a little more subtle, and there are actually a few possible solutions to this issue. So what I mean by multimodal behavior, just to give an example, is this. Let's say you need to go around the tree, and today I went around the tree by going left, which is a perfectly reasonable solution, and tomorrow I'm going to go around the tree by going right. Both of these are very reasonable solutions to the problem, but it's really important for me to understand when I'm standing right here that it's okay to go left and it's okay to go right, but it's not okay to average these two answers together. So you have multimodal behavior, and the multimodality really matters. So in some cases, multimodal behavior is actually no problem. If you have discrete actions, typically what you would do is you would put a softmax at the top of your network, which allows you to represent a full distribution over this categorical random variable, including multimodal distribution. So you can, if it's discrete actions, then you can put a lot of mass on the left action, a lot of mass on the right action, and no mass on the middle action, and that's perfectly fine. But if you have continuous actions, these things get a little more difficult. So the most common way to train policies that output continuous actions is to use a Gaussian distribution. If you're using a mean squared error loss, you're really using a Gaussian distribution because mean squared error is the log probability of a Gaussian. So if you're outputting either the mean or the mean invariance of a Gaussian, this is a unimodal distribution. So if you try to fit it to this data, you will get exactly the thing that you don't want. So you'll get this. So you have to be careful. You have to modify somehow the output of your distribution so that it can handle multiple modes. And we have a few choices for how to do this. And these choices all come with their own strengths and weaknesses. One choice is to not output a single Gaussian, but to output a mixture of Gaussians. This is actually probably one of the simplest, but also one of the least expressive. The second choice is to use latent variable models, and I'll explain those a little bit. This is a very general choice. It's mathematically quite elegant, but it can be a little complicated to set up. And the third choice is to use autoregressive discretization, which is maybe a little ugly in terms of how to set it up, but can actually be simpler than latent variable models. So let's talk about the mixture of Gaussians first. This is exactly what it sounds like. You're going to have your neural network outputting not just a mean and a variance, but it's going to output n means, n variances, and a weight, a scalar weight on each of those n entries. The scalar weights need to sum up to 1, so you need to put a softmax on them, and then the means and variances are literally just different heads of your network. So you have your big neural network, and it's literally outputting the parameters of a Gaussian mixture model. This is sometimes referred to as mixture density networks. It's a very simple design for a multimodal distribution, and if you have enough mixture elements, you can represent fairly complex distributions this way. The main way in which this design is limited, of course, is that you have to pick the number of mixture elements, and in general, for a finite number of mixture elements, you cannot represent arbitrary distributions. So in practice, what that means is that in low dimensions, if you have 1 or 2 dimensional actions, this design tends to work very well. If you have extremely high dimensional actions, then the choice of n might end up being very delicate. Let's talk about latent variable models. This is probably one of the more complex ways of doing this, but also a very general way of learning multimodal distributions. So the idea with latent variable models is that we're not going to change the output. The output will still be something simple, like a unimodal Gaussian. But what we'll do is we'll actually inject an additional input into the network at the bottom, which is going to be some kind of random number. So maybe this random number is sampled from a Gaussian distribution or a uniform distribution. The point is to give the network some source of randomness. And then we're going to try to train the network to use that randomness to actually change the output distribution. So for a little bit of intuition on this, maybe if you have this left versus right scenario, the network will learn that if the noise that's coming in is, maybe it's one-dimensional noise, maybe if it's negative, it'll go to the left. If it's positive, it'll go to the right. Now, that sounds very nice, and in fact, in principle, this is an extremely expressive technique because a neural network is a universal function approximator, so it can transform this noise into any distribution at the output. So that makes it very powerful, but you have to somehow get the network to actually use the noise. And in practice, that's where a lot of the challenges crop up, is how do you actually teach this thing to use that noise effectively to represent complex distributions? And there are a number of techniques in the literature. If you just inject the noise into the network and train it with maximum likelihood, it in general will not actually quite do the right thing. But if you're interested in these kinds of models, I would encourage you to look up some of these techniques that will teach the network to use the noise effectively. So you can look up conditional variational autoencoders, normalizing flow or real NVP, and Stein variational gradient descent. And we'll cover the variational inference and variational autoencoders towards the end of the class. Question?
So you're saying during inference, you also have to introduce
Yeah, so basically the issue here is the following, that if you're just feeding in noise just from the prior during training, the network doesn't really have any reason to use the noise because the noise doesn't correlate with the output. So for example, with variational autoencoders, what they'll do is they'll actually use a different distribution for the noise during training that gets to peak at the answer, and that teaches the network to use the noise. And then during testing, you just sample the noise from the prior. Normalizing flows, what they do is they actually use an invertible transformation for the neural network, which allows you to compute the log probability using basically the change of variables formula. And Stein variational gradient descent is a whole other kind of complicated beast that I won't go into, but I can talk to you about it offline if you like. So I'm not going to have time to cover these in detail today, but I just wanted to give you guys the keywords if you're interested so you can look these up. Okay, number 3, autoregressive discretization. This one is fortunately a lot simpler, but it requires quite a few changes to your network. So the idea behind autoregressive discretization is the following. With discrete actions, there's no problem. With discrete actions, we can just use a softmax and represent complicated multimodal distributions. With continuous actions, it's not so simple. So what if we take our continuous actions and we discretize? Well, we can do that. That's perfectly fine. It's just that if you discretize high-dimensional continuous variables, then you're going to get the curse of dimensionality. So if you have 2-dimensional actions, it's fine to discretize. If you have 10-dimensional actions, you're going to get so many discretization bins that you're going to run out of memory. So autoregressive discretization deals with this problem by discretizing one dimension at a time. So the idea is the following. We're going to take the first dimension of the action. Let's say our action is like 5-dimensional. We're going to take the first dimension and we'll discretize that first dimension. We'll do the usual softmax thing. And then we're going to sample from that distribution. And we're going to get a value for the first dimension of the action. And now what we'll do is we'll have another network where we'll give that other network this discrete sample and then ask it to predict a discretization over the second dimension conditioned on what we sampled for the first dimension. And then we just repeat this process. So then we sample the second dimension, get a value for it, and then we give both the first and the second dimension to another network that's going to discretize the third dimension. And then we repeat this until we've sampled all of the dimensions. At training time, things are very, very easy because at training time you know the values of all of these actions. So you don't need to do sampling at training time. At training time, you just literally have all these softmaxes. You have cross-entropy losses, and you give them the actual values of the actions. But at test time, you do this one dimension at a time, sample, and feed in the value to the network. And this will, in general, allow you to express arbitrary distributions over high-dimensional actions. Of course, you still have to discretize each dimension, so you get a little bit of discretization error, but you don't get the exponential blow-up in the number of bins. Okay, does anyone have any questions about autoregressive discretization or any of these other techniques? Yeah?
So all of the other actions, the input to the network is just the previous action? Or the previous
dimensions, yeah. And you can do it in 2 ways. In general, the strictly correct way to do it is you have to feed in all of the previous dimensions. So this little network should get dimension 1. The network that follows should get dimension 1 and dimension 2. Sometimes people will just feed one dimension at a time, which technically assumes some independence between the dimensions. That's not quite correct, but if you feed all of them, then you're good. Yeah?
So the image is actually not refed up to the additional neural nets?
Typically it is,
Okay.
yeah. It just, I was a little sloppy in drawing it here, yeah.
What are some disadvantages for autoregressive?
Yeah, so the main disadvantages for the autoregressive discretization, first, it can be a little difficult to set up because you have to modify your network substantially. And it's not like the mixture density network where you just have more outputs. You have to actually build these networks and figure out how to wire everything together. And there's a little more architecture design that goes into it. And second, you do get some discretization error. So if you really want really fine, precise values, you need to pick the right number of bins here, and that can be a little delicate. Yes?
So you said like these additional networks share parameters, or they are like
No, in general they don't. You could share parameters. You could use an RNN, but in general you don't need to.
But how does it deal with that curse of dimensionality? Like every dimension that you add is going to be another.
So it's linear in the dimensionality. The curse of dimensionality refers to exponential in the dimensionality. Here it's linear. So the network does get bigger, but linearly. Yes?
So we train separate networks, or do we train end-to-end?
This whole thing is trained end-to-end because at training time you don't actually have to sample. So at training time you know the value of these actions. So the difficult thing about sampling force is you can't backprop through sampling very easily, but you don't have to at training time. At training time, you know what values these should take on, so you just have a cross-entropy loss here and a cross-entropy loss here and so on. Yeah?
So is there any clever way to pick the dimensions, order of the dimensions, or is it just
Not that I know of. It's, to my knowledge, people always just kind of make something up. Okay, let's continue. So just to recap our discussion of imitation learning, it's often, but not always, insufficient by itself. So if you just do the naive thing, usually it won't quite work. You get this distribution mismatch problem, but sometimes it works well. Sometimes it works well because you have hacks, like you figured out that if you give it the left camera and the right camera and change the action around, it'll kind of stabilize this thing. You can maybe figure out some way to sample from a stable trajectory distribution. Maybe you have access, you can actually like inject noise into the demonstration, or if you're imitating like a planner or optimal controller, you can force it to correct noise, and that'll teach you how to recover. You can add more on policy data, for example, using Dagger, or you can design better models that actually fit the data more accurately by trying to understand what are the common pitfalls in imitating human data. So you can make it work very well, and in practice, with a bit of effort, imitation learning can work very well. Okay, I think I'll skip the break today because I'm running a little behind and have a lot of stuff to cover, but the next part is all videos, so it'll be a little more relaxing. Now that I went through a lot of the technical material, I want to show you some examples of papers, research papers, that have used some of these techniques to do interesting things. So the first one I'm going to talk about is this paper called The Machine Learning Approach to Visual Perception of Forest Trails for Mobile Robots. And I'll just start playing the video and I'll talk over the video. So what these guys want to do is they want to get a quadrotor to fly down a forest trail. So the objective is you have to follow the trail, not go off the trail, not hit trees, and not do anything terrible. And they're going to do it with imitation learning. So this is a video of their quadrotor happily flying through the forest somewhere in Switzerland. It's autonomously following the forest trail, but of course they're going to have to deal with that problem, the distribution mismatch problem. The way that they're going to deal with the distribution mismatch problem, you're going to see that in a second. So they're just flying using a monocular RGB camera. I don't think this is the main challenge, but it is a challenge. So it's, yeah, they have to deal with complicated images of very scenic Swiss countryside. And their action space here is just discrete. They're just doing left, right, straight. So that makes it nice that they don't have to deal with any of these multimodality issues. It just falls out for free. Just 3 output labels. And yeah, they're just like that. So the cool thing is how they're going to deal with that drift problem. So they're actually, okay, so their classifier is a big connet. They're not actually going to fly the quadrotor by teleoperation. In fact, their training data doesn't even come from a quadrotor. The way that they get their training data is by getting a person to generate the data for them, which in the process also gives them a really neat solution to the drift problem. There, so they get a guy with a headband and 3 cameras. And then they do exactly what you expect. So the left camera is labeled with right, the right camera is labeled with left, and the front camera is labeled with straight. And this is a view from a guy walking with 3 cameras on his head. And that's it. And that's what they're going to use to then train their network. And because you get these left images that are labeled with right and right images that are labeled with left, that actually teaches the network to stabilize itself in the middle of the forest trail. So this is actually even simpler than the NVIDIA work because the actions are just discrete, and the main downside is that you look kind of silly while you're collecting the data. Okay, so that's kind of neat. I mean, it's sort of an engineered solution, but it's a very, very simple solution, something basically anybody could try. Here is another example that I wanted to describe. This is a robotic manipulation work. And here, they're opting for that last class of solutions where you're going to design a powerful enough model so that it doesn't suffer very much from these drift problems. And in particular, what they're going to use recurrent neural networks to deal with the non-Markovian nature of the demonstration, and they're going to use mixture density networks, these mixture of Gaussians models, to deal with the multimodality. So the kind of tasks that they do, they're going to do robotic manipulation tasks. So they're going to have their robot, this is just teleoperated by a person, I think, oh, this is actually the policy. Okay, so the policy is trained from teleoperation by a person, and they're going to have it picking up objects, moving objects, putting them on a shelf, and things like that. So these are things that do require, considerable coordination, because you have to make sure that the fingers are placed actually on the object, not just close to it. So you do need some degree of precision. And the nice thing is that they can actually intentionally ask the human demonstrator to not be perfect, to make some mistakes, just so that they can illustrate corrections to those mistakes. So that's why you saw that when it dropped the box, it actually went and picked it up again, because during training, they actually asked people to intentionally make some mistakes just so they could see corrections to those mistakes. And then they can kind of run on a real robot, and the robot will fumble around a little bit, but eventually get the box and actually put it on the shelf after a few false attempts. So this is, at this point, not operating on images, but they do have a follow-up work that does do images that I'll show shortly. But first, I wanted to show you the design of the network. It looks more complicated than it is, but it's basically 3 layers of LSTMs, outputting the parameters for a mixture of Gaussians. So it has recurrence, it has the multimodality from the mixture of Gaussians, and then they compare to alternative designs, including networks that are feed-forward, networks that are recurrent but don't have the multimodality, and networks that have the multimodality but don't have the recurrence. And they find that their thing, which has both recurrence and multimodality, does indeed do better. The multimodal feed-forward thing is kind of decent at one of the tasks, but really terrible at the others, and the rest are worse. So this is kind of analyzing the effect of both the multimodality and the recurrence. And this is their follow-up paper that also includes image observations. So they have inputs from a camera going through a convolutional neural network. One of the things I really like about this paper is that it's like a very low-cost setup. So they have this this is, I believe, a Lynx Motion arm. It costs about $300, and this is a video game controller, which they're using to provide demonstrations. So here they're just illustrating their demonstration setup. This is a guy using a game controller to control this arm, and that's going to generate data. And the data here is a few hundred demonstrations per task, and there are, I think, on the order of 10 tasks. And then they're going to use that to train their model, which has, in this case, a convolutional network to process the images, recurrence for the non-Markovian stuff, and the mixture density model for the multimodality. And it's going to be doing all sorts of things like picking up cloth and wiping down a box of screwdrivers. So that's kind of cool. And the neat thing about this that I like a lot when you watch these videos, you notice that sometimes it'll kind of screw up, it'll try to fix itself, it will do things like a certain number of times. So it was taught to wipe down the screwdriver box like 4 or 5 times or something, and it actually does it that many times. So there's some pretty cool things going on here. And this is all just like running continuously. Okay, so that's imitation learning in a kind of a robotics setting. Other things where imitation learning can be important. Aside from the kind of control type things that I discussed in this lecture, imitation learning, including algorithms like Dagger, come up pretty often in structured prediction. So structured prediction problems are problems like machine translation, where your output has structure. What kind of structure? Well, let's say that you're doing question answering. So you have a question that comes in, the input is, where are you? And the output is, I'm at work. Now, when you're constructing the answer, maybe you're using a recurrent neural network to do this, you don't just want to match the tokens individually one by one, because the tokens have a lot of dependencies in them. So if you start outputting, I'm at, then you should finish by giving the right answer, which is work. But if you messed up on the second word, if you said in, then putting work as a third word is actually a bad idea, because even though it's the correct word, it doesn't go with the second word. So the probability of I'm in work is actually much lower because of the correlations between the outputs, irrespective of the input. So this is just violating your language model. So especially in machine translation, this kind of stuff can be really important. So maybe you don't want to put work here. If you put in, maybe you want to put some other word. I guess you can put in school, this is grammatically correct, but it's maybe not a truthful answer. But the point is that when you have these correlations between the outputs, you might actually choose to treat this problem as a sequential decision-making problem. And techniques like Dagger can actually help you do a better job of solving these structured prediction problems by basically asking humans or asking your ground truth kind of generator to provide you with the right actions to take when you make mistakes earlier on in the sentence. So in fact, techniques like Dagger have been used extensively for structure prediction problems, and this is also discussed in the original Dagger paper quite a bit. Another thing about imitation learning is that all the discussion today focused on imitation learning in the kind of policy learning setting, where your goal is to take data and figure out how to output the right actions given an observation. But you can use demonstrations for other things too. You can, for example, use demonstrations to figure out what somebody's goal is, and then use regular reinforcement learning to figure out how to achieve that goal. So inverse reinforcement learning deals with that problem. It's basically, instead of copying the demonstration, figure out the goal, and then use some other learning algorithm to figure out how to achieve that goal. Maybe you can actually achieve it better than the demonstrator did. So we'll cover inverse reinforcement learning later on in the course, and there's quite a bit of interesting kind of analysis we can do there. So what's the problem with imitation learning? Why can't we stop here? Why do we have another, 13 weeks left in the class? Yeah, I guess it's because we all need to, you guys need grades and I need to get paid, so maybe that's why. But there is a deeper reason. Humans need to provide data for imitation learning, and that data is going to be finite, right? So even if you have $1 million to spend, there's only so much data you can get for $1 million. Deep learning works best when data is very plentiful. In fact, oftentimes when we've seen big advances in deep learning technology, like in computer vision or speech recognition, those advances have been accompanied by large increases in the amount of available data, going from like CFAR to ImageNet. So deep learning works best when data is plentiful, which means that in practice, oftentimes the amount of data you have is actually the bottleneck on the performance of your system. So it'd be awfully nice if the performance of our system wasn't bottlenecked by something quite so expensive. That's maybe one of the deeper and more philosophical reasons, but there are also very practical reasons. So humans are good at providing certain kinds of demonstrations, but are not good at providing certain others. So maybe a person is very good at walking down a forest trail like this and helping you figure out what's left and what's right. They're kind of okay at teleoperating a vehicle or like flying a quadrotor. They're not very good at like low-level stuff like telling you how fast the rotors themselves should spin. So probably if they're using a controller to fly a quadrotor, that quadrotor has to have some kind of low-level autopilot to actually figure out which voltage to apply to the motors. People can't pick voltages by hand. And if you ask them to teleoperate like a huge robot like this, okay, maybe for this you can get a really costly sort of rig with kind of a harness and so on. But what if this robot has like 8 legs and 20 arms? Now you need like a whole team of people to teleoperate it. And what if you're trying to get your machine to do something that people aren't even very good at? What if you want your machine to beat the world champion at Go? Well, then the kind of doing it by imitation almost defeats the purpose. So there are some things where people are very good at providing demonstrations, where it makes a lot of sense to use, and in some settings where it's just a very difficult approach to use. And then, of course, there's kind of the more conceptual, maybe the more philosophical way of approaching it, which is that humans can learn autonomously. Even if you think that people learn a lot from imitating others, clearly there are some things that we can figure out on our own. So wouldn't it be awfully nice if our machines could do the same if we're really taking this idea of building intelligent machines seriously? So we can get unlimited data from our own experience. We don't need to rely on others. And if we can learn autonomously, that we can improve autonomously and continuously. We can keep getting better and better without having to ask anybody for help. So we're going to really get into autonomous learning and reinforcement learning starting next week. But one thing that I want to introduce today is the notion of an objective. So once you get away from imitation learning, in imitation learning, the objective is simple. You have to just copy what the person did. If you're learning autonomously, you need some other kind of objective. So if I'm back in the jungle here where I'm seeing my favorite tiger, maybe my objective is not just to copy what my friend did. Maybe I'm not even going to worry about the policy right now. Maybe my objective is to minimize some adverse event that I don't want. Maybe I want to minimize my log probability of getting eaten by a tiger. That's a very reasonable objective. That's actually what I'm probably after a lot more than I care about imitation. So in general, when you're learning autonomously, you need to formulate some kind of cost function or reward function that describes what you want. So this log probability of getting eaten by a tiger, this is my cost function. Or you can also think of it as the negative of my reward function. So the two additional pieces of terminology I'm going to introduce, C of ST80 is a cost function, R of ST80 is a reward function. They're basically the same. One is just the negative of the other, and that's actually going back to these guys. So in control theory, you'll often see people talking about cost functions and using L or C to denote them. In reinforcement learning, usually we use reward functions. You want to maximize rewards or minimize costs, and maybe this reflects some sort of national bias. Maybe Americans believe they'll get lots of rewards, and Russians believe they'll have regrets and costs. But that's the way it is. So if you see C, don't worry about it. It's just the negative of R. That's it. Okay. So now that we know about rewards and cost functions, there is a little bit more analysis that we can do on imitation learning, because now we can say, okay, well, what actually is the cost function or the reward function for this imitation learning business? Can we actually formulate a notion of optimality? Like if Dagger is solving a problem, which problem is it solving? So going back to imitation learning, there are actually a few very reasonable choices for cost or reward functions. For example, we can say the reward function in imitation learning is the log probability of matching the expert's action. That's actually a very reasonable choice for a reward function. This is a log probability. You can make it into a cost function too by taking negative log probability, negative log likelihood. You can also have a 0-1 loss. You can say, well, maybe you pay a cost of 1 if you make a mistake and a cost of 0 if you match the expert. Or you can have a reward function, which is 0 if you match the expert and negative 1 if you make a mistake. So either way works. And this basically is analogous to a 0-1 loss in supervised learning. So Dagger can actually be shown to minimize loss functions of this form. Which one you pick depends on which loss you're using when you're training. But for the analysis that I'm going to show, we're going to actually go with a 0-1 loss because it just makes the notation a little bit cleaner. You can do the same thing for any convex loss, though. So let's do a little bit of analysis. And I have about 10 minutes left in the class. This is not going to be very, very heavyweight analysis, but there's just a little bit of algebra. So let's go back to this distribution mismatch problem. So we talked about how part of why regular imitation learning without Dagger might cause you some trouble is that you have two different distributions of our observations, p pi theta of O and p data of O, and they're not the same. So how bad is the problem? So intuitively we talked about how you make mistakes and then you make bigger mistakes and so on and so on. How bad is it? Can we somehow quantify or bound how bad it is? So we're going to use capital T to denote the length of our trajectory. So capital T is a horizon. It's how long we're going to act for. In general, capital T might be infinite, in which case we need to do a little bit more algebra. But for now, let's just assume that capital T is finite. It's a finite number, so you're going to be like driving the car for 1 hour. And let's analyze the case of the 0-1 loss. So basically, you're paying a cost of 1 if you don't match the expert at a particular time step and a cost of 0 if you do match them. This makes things very simple. And now what we're going to do is we're going to construct a problem where things are going to be pretty bad if you do direct imitation. Now we have to assume something to begin with. We have to assume that something about the imitation learning process is reasonable. And one thing that we really like to assume is that you do well on your training set. So we're going to assume that your training algorithm is not completely broken. We're going to assume that your probability of not matching the expert is less than or equal to epsilon for any state that you saw during training. This is a reasonable assumption. This is just saying like you didn't screw up in setting up your learning algorithm. On the states where you trained it, it's going to do well. It's going to have a small probability epsilon of making a mistake. But on states that you didn't see, all bets are off. So what we're going to do is we're going to set up kind of a pathological domain where this thing really causes us a lot of trouble. It's going to be kind of like a tightrope walker domain where if for the tightrope walker, if he takes the right action, he's all good. But if he messes up even a little bit, then he falls off the tightrope and he's in a completely different place. And at that point, he can never recover. But this is a very strange tightrope walker. This tightrope walker doesn't actually care about falling. They don't feel pain. What they feel is 0-1 loss. So that means that the biggest concern this guy has is failing to match the expert. And the only reason that falling is bad is because he doesn't know what the expert did when the expert fell, because the expert never fell. So here is a schematic illustration of the tightrope walker. This is kind of a grid roll domain, so in each cell you can go up, left, down, or right. And you're going to want to stay on the tightrope, the gray thing, and if you go in the red stuff, you will have never seen any data there. So what you want to do is you want to keep moving to the right, and if you ever go up or down, you'll find yourself in these red states that were not in your training set, and you will not know what to do, and therefore you will incur a cost of 1 because you'll almost certainly mess up. So let's start analyzing how bad this is going to be. What is going to be our cost? So the thing that we care about is the expected value of the total cost. So the sum of the costs over all the time steps from 1 to capital T. What is the probability that you will make a mistake on the very first time step? Assuming you start on the rope. Yes?
Less than or equal to epsilon.
Less than or equal to epsilon. And we'll be pessimistic. We'll say if it's less than or equal to epsilon, it's actually epsilon. So the worst possible thing that can happen. So on the very first time step, you make a mistake with probability epsilon, and if you make a mistake, you're going to be in this red state, which you will never leave because you can't fly back up onto the rope. And then you have T more steps to go, so you'll keep making mistakes every single one of those T steps. So the cost you'll incur if you make a mistake is capital T, so that's 1 times T, times the probability of actually getting there, which is epsilon. But now you have the rest of this. You have 1 minus epsilon times all the rest that can happen. So you have 1 minus epsilon, that's the probability you go to the next state, and there you again have an epsilon probability of making a mistake, at which point you fall into one of the red states and keep making mistakes for T minus 1 steps. And then you keep going like this. And then you have another 1 minus epsilon times T minus 2, and so on and so on and so on. So you're going to have T of these terms, because there's T steps, and each of these terms is going to have a cost that's on the order of T. It's going to be like T, T minus 1, T minus 2, T minus 3, etc., but that's on the order of T. So T terms that are each O of T, and each have a multiplier of epsilon in front of them, that means that your total cost is on the order of epsilon times T squared. Now epsilon times T squared is very, very bad, because in general, we might want to solve temporally extended problems, and this is saying that the more temporally extended it becomes, the more you pay, and you're going to pay quadratically. So even if epsilon is very small, for a long enough trajectory, you're going to pay a heavy price. Okay, does anyone have any questions about this? Okay, so this is a very simple analysis for a very kind of simple discrete environment. Now, in general, we don't want to make assumptions that are quite like this, because this assumption that you're only bounded by epsilon literally in the states you saw in the training set, that's a very weak assumption. We know more than that. We know, like, supervised learning algorithms basically work. So we know that supervised learning algorithms, when provided with enough training data, actually generalize. They generalize to other samples from the same distribution. So we can make a slightly stronger assumption. We can assume that your error will be bounded by epsilon for any states sampled from the training distribution, even if it was not identical to one of the training states. And this is very important because in a lot of practical problems, like let's say you're driving based on images, you're not going to literally see the same image twice, but you might see images that are from the same distribution that are similar in various ways. So in general, we'll actually want to make a stronger assumption like this. We'll assume that our error is bounded for any sample from our training distribution. And we can actually repeat the analysis we did on the previous slide. It'll be a little more involved, and I think I'll probably go through the analysis of the bad situation next week. But what I do want to conclude with here is a very, very short discussion of what happens with Dagger. So with Dagger, P train is going to approach P theta of S, so the distribution mismatch will go away in the limit once you collect enough data. And once the data goes away, once the distribution mismatch goes away and the data distributions match, then all of the samples you see will look like samples from P train, which means that your error will always be bounded by epsilon at any single time step. So does anyone have any guesses as to what the bound for the total cost with Dagger is going to be at convergence? So all of your states that you see are from the training distribution. Your error is bounded by epsilon on states from the training distribution. Your horizon is capital T. Yes?
So order epsilon T?
That's right. So the order will be epsilon T. Because you'll have T time steps. Each time step you have an epsilon probability of making a mistake. So it'll be bounded by epsilon T, which is the best that you could possibly do. If you have T time steps and you have epsilon probability of making a mistake every time step, there's no way you could do better than this. So in the limit, when the distribution mismatch goes away, all the problems are gone. And then the interesting thing happens if we want to analyze the case where the distributions don't match. I'll go through the full derivation of this actually next week, but as a quick preview, when the distributions don't match, you can actually derive the bound of epsilon times t squared, just like on the previous slide, except that now we're dealing with distributions, so the math is going to be a bit more involved. So I'll present that on Friday next week. And then on Wednesday next week, just as a reminder, Greg Kahn will be giving that TensorFlow tutorial, so do make sure you get started on homework 1. And if you find that you're having some trouble, absolutely make sure you go to that lecture and ask Greg lots of questions.